So next we have Ted Marena from Western Digital on Embedded RISC-V Core for storage applications. Ted is a senior director at Western Digital, and he's responsible for evangelizing the RISC-V, accelerating the build out of the RISC-V ecosystem, and marketing machine learning solutions and zone storage initiatives. Ted is the marketing chair for RISC-V Foundation and is also the managing director for open source hardware development organization, CHIPS Alliance. In our last meetup, we talked a little bit about the CHIPS Alliance and the RISC-V Foundation and so forth with our members. So with that, Ted, it's all yours.
Okay, great. So let me steal the ball and I'll share my content. Put that there. Okay. Yeah, so I really I'm pleased to be able to present today. It's something I've been involved in RISC-V for quite a while. Hopefully this will just share. Okay, you guys should, let me make this bigger. I got involved in RISC-V back in the end of 2016. I attended my first event and it was, you know, really eye-opening for me. Hold on, let me just swap the displays. Okay, so you guys should be able to see the presentation. All right, so I've been involved with the foundation, which is now called RISC-V International. It's a global organization, open to everybody, really. And what I want to talk about today are a brief history on RISC-V. I think there may be some folks in the audience who aren't really either on board with RISC-V or up to speed. So I just want to show a few slides on that. And then I'm going to get into what it is about Western Digital, why we got involved with RISC-V. Then talk about some of the challenges that we think RISC-V helps us overcome. We'll go into the RISC-V Swerve cores. So these are Western Digital's, the RISC-V cores that have been open sourced. And just give you a few details on microarchitecture and some other points. And then sort of, you know, show you how we see it fitting together in embedded applications for us. Around storage, and then wrap up. So I'm happy to take questions. I would say if you put them in the Q&A chat, I'll poke up my eyeballs every once in a while to take a look at that. And I'm happy to either answer them by typing or you can interrupt me. So if you see something come through, Kundan or John, just, you know, flag me if I'm going on and on. Okay, so what is RISC-V? And I think when I started to talk with people back a few years ago, people thought it was a processor architecture, and it's not a processor architecture. It's basically, it's an open instruction set architecture. So I must have animation on, and that's going to drive me up a wall. So let me just do this for a minute here and not have the screen be moving. I apologize. So the RISC-V is a specification. So you basically have a number of commands and there's a minimum base set of specifications that you have to implement. And then there's a number of extensions that are optional that you can implement. And one of the things that really started to build momentum for RISC-V, and I'm going back to 2014, 2015, was when the specs were frozen. So the instructions were frozen, which meant if you wrote software for RISC-V, they're frozen, so it's going to run on RISC-V forever. And that's very compelling for a lot of applications that need to rely on architectures for long periods of time. What tends to happen with the proprietary processors that are out there is they keep getting instructions added every generation. You know, one of the new customers or a big customer wanted it, so they add these instructions, and then everybody, to stay up with the latest architectures, you got to recode, recompile. You have to do a lot of work, new validation, and I think RISC-V affords a real fresh reset of that paradigm. So I mentioned that you have optional instructions, so it's modular. So you don't have to implement everything, right? It's kind of like going to a restaurant and ordering exactly what you want. You don't just have to get the blue plate special. So you can, choose the extensions and functions exactly what you need. It's also doesn't have any baggage, which is sort of one of the big advantages, right? It's a clean slate architecture. It doesn't have to support code that was written 20 years ago. So there's sort of an inherent simplification to that. And then the other thing, which is kind of cool, is you can do custom instructions. So those are potential leverage points of what people might do to further differentiate their products and technology. All right. For you guys that maybe are on the call and you maybe have heard of RISC-V, but you don't see it's super prominent. I think there's a couple of really high-profile announcements or activities that you may or may not know about. Microchip has a architecture that's called PolarFire SoC, and this is actually an FPGA family, but they added a quad RISC-V processing element to it. And it supports Linux or real-time can run both. So, they kind of one of the first positions is military aerospace, but the family actually can support a lot of different applications. They are going to be announcing hardware. They talked about it at the RISC-V Summit back in December. But they should have availability, and I think that's going to be a really exciting point for the market because it's really the first lower cost Linux capable RISC-V architecture. There's a lot of other announcements. Companies like Alibaba, Sony have introduced cores or talked about going to introduce them. Greenwaves is a really interesting company. It's a startup. It's based out of Grenoble, France, that has the ability to run on battery for a long, long period of time. And they have a lot of the scalable performance. So extremely efficient architecture based on RISC-V. You may not have heard of them. Facebook's Oculus is doing some RISC-V and embedded applications for their parts. Huami's is a company that makes a number of wearables. They have used RISC-V. And also back in December, Samsung did a keynote at the summit, and they had announced that they were using RISC-V in some of their 5G infrastructure. So it's a kind of I wanted to show a smattering of what is really out there. Okay. So,
Jed, there was a question about,
okay.
if you know this, there was a question if PolarFire was a 32-bit or a 64-bit core.
Yes, so I do know. So it's four 64-bit cores. So if you go to Microchip's website, you can see it's a quad 64-bit architecture, and it supports, I think, virtually every extension except maybe it doesn't do quad floating point or something, but it's a quad 64-bit implementation. The thing that I like to point to is a market research that Semico had put together, and they had worked with a lot of RISC-V organizations, but also their own data mining and contacts in the tech world, and they actually see up to 62 billion cores over the next 5 years that will ship. So these are basically, a lot of the initial usage of RISC-V is embedded cores, similar to what I'm going to show you that Western Digital is doing. A lot of companies companies like NVIDIA, other organizations like Samsung and so on, they embed, they have these smaller controllers that are inside the device. And that's a lot of times how people get started. And then all of a sudden, as the ecosystem grows more and more, you're going to start to see external exposed architectures like the Microchip one, like the Greenwaves and so on. But you can see significant growth here in a number of different markets, and this may be kind of hard to see, but industrial is a big chunk of the market. With some in like small sliver in transportation, communications, compute, consumer. Let me try to go back to full screen and see if I can just keep going here. It might be easier for people. So we have more than 570 total members. Because individuals can join, I tend to focus more on the organizations, companies, and technical organizations. And we have over 200 of those. And so you can actually see it's been a tremendous growth. I got involved and started, get interested in RISC-V around this time. There were some key inflection points when Western Digital had made an announcement at the end of 2017 that they were going to be moving their devices to RISC-V. It provided a lot of momentum, and you can just see things have continually, moved in the up and to the right. So we are really excited about the breadth and the support that the ecosystem and the membership are contributing to make this very successful and wide-reaching. Okay, so that's just kind of a background on RISC-V, RISC-V International, sort of where we're at. And if you go to riscv.org, you'd see a number of, more things. But what I want to talk a little bit more about is, Western Digital and, sort of what we've been doing. And I think what I'm going to do is actually, I'm going to, well, let me just sort of go here, and then I'll show you all the things we have been doing, and then I'll talk about why. And I think it provides a really interesting, sort of understanding. And there's a couple different reasons, but we have, started, way back in 2014 to 15 timeframe. We joined as a founding platinum member. Starting looking at different solutions, and there was a couple of different reasons, which I'll show you on the next slide, why we started getting into it. And we've been doing a lot of different things. We've been developing cores. We've been working with tool vendors. Platform.io in particular has a terrific web interface that supports a number of different architectures, not just RISC-V. They support other architectures, but you can take your code, your C code, compile it. They target boards. They have a lot of capability that makes it easy for you to move and try your software on RISC-V. We've been doing a lot of upstreaming on Linux. Whoops, sorry about that. Okay, no, I have no idea why it does that. I'm just going to keep rolling with the punches, though. We've been working with Linux. We've been working on code density. So this is something that's really important for us. The amount of memory that it takes to store and to run the code, we want to have that as small as possible. And when we started getting involved in RISC-V a few years back, the code was larger than a lot of the current architectures. So, that's kind of a disadvantage if you have to buy more memory to store the code. And we've worked a lot with a few different companies. And this is something that, now is on par and actually starting to get better than competitors. So just to show you what we've been doing, because really at the end of the day, we're looking to create data-centric architectures and incorporate RISC-V into, a number of devices, which, some of our devices have one core, but some of them have 2 or 3 or more. And, if we ship and convert all of the architectures, it would be more than 1 billion cores. So we're on our way. But of course, it takes a while to do hardware. So when people ask me why RISC-V for Western Digital, there's really 3 points that I like to sort of say. One is, it's actually a long-term bet for us to make sure that open standard interfaces continue to exist. And you can just see from this picture here, Intel had a dedicated proprietary path for their persistent memory called DDRT. And even though they've been talking about removing this, it's still on their architectures. Nobody else is allowed to license that bus. And, that's a huge threat because we make storage kind of products. So, this is something where we want to participate. They don't open up their coherency bus. There isn't really a processor vendor that does, but we believe for memory-centric architecture, this is really important. So, this open standard interface is actually a big reason why Western Digital got involved in RISC-V. Well, as we look at it for our products, we believe it increases innovation. It allows us to actually, we think, get to market quicker, and will allow for product differentiation as we move forward because we control the architecture of the implementation. And I think, also for us, this is a way to really show all the tremendous R&D innovation that's going on in Western Digital, and it's a kind of a window in to what the company does, and I think it fares very well, and it really shows exactly what's happening. Okay, I'm going to look at this question. Does Western Digital have a RISC-V SoC running Linux? So the answer is no, we don't right now. So that's the short answer to your question. And because I don't want to get into trouble, I'm going to just keep going. But that's the answer, Drew. Thanks for asking. I want to sort of now shift gears and talk about, what is it that we have challenges for a flash controller as an example. So, the previous architectures where we're using, I'm not going to name what they are or who they are, but we struggled with these issues. One is the number of instructions per clock cycle. In other words, how many instructions can you execute for each clock cycle? We also, branch prediction is something that's also a real challenge is, if you don't have really good branch prediction or control and how you do the branch prediction, then you're going to be, constantly having, to go to external memory. And instruction cache hits. So we wanted to, improve this as well. So these were issues that, because we had to pick an external architecture before RISC-V, we were constantly asking vendors to work on these things, but these were not necessarily priorities for them. And so, when we had introduced our SWRV architectures, especially our initial core, the SWRV EH1, we were able to, for actually a smaller architecture, have about 2x the improvement in instructions per clock cycle. Our branch prediction was about 50% better, and our cache hits improved performance about 40%. So, these are some pretty significant numbers that, as we were doing evaluation, were not only important to us, but, we could get some concrete information behind. And what was interesting is, we put the first cores out, and then some of the other business units would look around and talk about, hey, we have other applications, and some of these other applications need multiple processors. But what was interesting is they said, if we had a dual-threaded architecture, a lot of times one processor is going out making an I/O call, so it's just sitting there twiddling its thumbs, and the other processor is executing something. And then when that does an I/O call, it's just sitting there. So they talked about a dual-threaded architecture. And so that was one of the demands. And then we had other requirements where the SWRV EH1 was just too big. So, hey, we want a smaller core. Instead of having fixed sequencing logic or state machine type of logic, if we had a small core, moderate performance that was teeny, we could convert a lot of that and then have more flexibility, and again be able to get to market a little quicker because you don't have to have full validation on some of these waveform shaping and other logic functions. And so as we introduced the latest SWRV devices, which I'll show you more details on in a second here, we introduced the world's first dual-threaded embedded core. And I remember when we were putting together our keynote in December. And we were talking about this as, you know, something that's like, duh, why didn't anyone introduce this before? You know, you have multi-threaded architectures that are Linux capable and multi-threaded x86 and so on and so forth, but nothing in the embedded space. And again, that's the beauty of RISC-V. You control the microarchitecture. You can implement these types of things. So, you know, it's really exciting to have been part of Western Digital, as we were the first company to commercially introduce a dual-threaded architecture for the embedded market. And that core is available to you all, which is the other part that's really cool and we believe will help accelerate adoption. The footprint, the architecture, as I mentioned, is actually smaller. One of the other benefits that we got was our development team is starting to see a time to market advantage, because we can control and do these things, and as opposed to in the past, we had to go to the IP vendor and either convince them or pay them to make the changes that we requested or wanted. So anyway, the point here is that the orangish color is meant to represent the EH2, and the bluish color here is the EL2 core. And when you look at kind of where we are today with our RISC-V cores, the swerve cores in particular, we first introduced the EH1. That was introduced in early 2019. And then we announced the dual-threaded EH2, as well as the smaller EL2. Those were announced at the summit, and they were open sourced in 2020. So you can find, this is the link for the EH1, the EH2 and EL2. I think you just have to put dash EL2 dash EH2 on that. And I apologize for not having that link in there, but I'll throw that in. Actually, a question I had for you, Kundan, are you planning to put the presentations in a folder somewhere, or like if people want these, or like, is that something you were thinking of doing? You're on mute.
Sorry. Yes, I can share those with everybody who's registered.
Okay. Okay. The other thing I just want to point out about these core, two other things. One is they're in an organization called CHIPS Alliance, which Western Digital is part of, and also other companies like Google, Esperanto Sci-Fi, other companies are participating and doing open source development. So that's the GitHub location that you find for the cores. And we also have been working with an IP company called Codasip that's actually doing some commercial support for these cores. Okay, so I'm just gonna sort of continue on here. I put the slide in here because a lot of times people say, what's the swerve? What's the deal with swerve? And so, you know, basically to explain this, the SW here, actually, well, swerve itself, you know, the definition actually has an E on the end, you know, to turn aside from a straight path or established pattern, right? So that's kind of what we did with RISC-V. We were using architectures that were, you know, in the market for quite a while, and we decided to go a different way. So that's the kind of the definition. The WE, the we really represents, actually, this is maybe where my animation might come in handy. So yeah, the we represents RISC-V and the first two letters of Western Digital. And then the RV obviously stands for RISC-V. So this is the first slide where animation helped me. Anyway, that's what Swerve is about. All right, so I want to get into a little bit on the architecture. Just go into a little bit of detail with the device and give you kind of an idea of, you know, what is the architecture. First of all, I'm going to start from the bottom here. This architecture scores 4.9 core marks per megahertz. So we have it implemented in FPGAs. You know, we've run this We actually did make a public statement that we had taped out the first SoC that's going to be used internally with the EH1. So that was something we had talked about. But the architecture is a 9-stage pipeline, and it uses what's called a dual superscalar architecture, and that's why there are these 2 sets of pipes that you see here. And the idea here is that you can, you have these various points that you can stall at. We have some things that are out of cycle, like the multiply and the divider. And the idea of this architecture was to be able to, to keep this pipe filled as much as possible. So earlier I talked about the number of instructions per clock cycle. I'm going to show you some data on how we have that improved. So this was the first core that we did. It was kind of a walk before we run. And, we basically, the next cores, the EL2 and the EH2 were built off of this. So the simpler core, the EL2, this is, again, based on the EH1. We added some bit manipulation commands. It's a 4-stage pipeline. So again, it's a simpler architecture. It's just drawn here, showing you it's got configurable instruction cache. There's closely coupled memory that you can use for data or instructions, and a number of generic AXI type of buses for peripherals and such. So what's interesting about this, even though this is a pretty small, only 4-stage pipeline, it still scores 3.6 core mark per megahertz, which is quite respectable given the small size of the architecture. So this is more of a general purpose kind of, either doing, replacing state machines, doing some initial startup, watchdog functions, maybe, trimming, those types of applications. That's really, it's designed as a very low-end housekeeping core. Okay, let me just see. I saw a question come over here. Are the ZBB, ZBS instructions WD's own instructions or part of some RISC-V extension? So they're not our instructions. They are part of the bit manipulation instruction set. And I believe, I want to say that's the B extension. So, RISC-V has a number, like you see this, for those of you who are not familiar, where's my mouse? Oh, God, okay. You see this IMC. So the swerve cores, they have integer, multiply, divide, and compressed instructions. So those are the extensions that we support, and these commands here are part of the bit manipulation extension. So that's the answer, Peter, for that. What guided selection of those bitmap instructions? I do not know that answer. I am sure there's a good reason. It was probably influenced by our firmware engineers, but I don't have the exact answer on that. I'm happy to follow up after. If it's something you would like to know, Drew, I can get you to the right people. Okay, I appreciate those questions, though. Let's talk a little bit more about the EH2. So the EH2, again, it's based on the EH1. When you look at it in this diagram, it looks very similar, and the reality is it is very similar. But what's different here is that there's like 2 sets of these various registers and control functionality that allows 2 software threads, if you will, to run simultaneously. So they can't necessarily all the time operate that way, but they are able to, in a more quick manner, have multiple instructions be operated. So we're seeing gains of up to 2x. And what's interesting is when the single threaded instructions per clock cycle is 1 or less, we're getting a really good boost. Obviously, the number of instructions, if the EH1 you know, operating higher than that, then as you're getting more efficient, it's hard to get more of a boost. And I'll show you like a chart on actually how efficient the core is. It actually scores 6.3 for core mark. So again, it's kind of a superset to the EH1. Of course, not every application needs it. It is larger. I think it's about, because they're targeted for different geometry. The EH1 was targeted for 28, and the EH2 was targeted for 16. But if you had them on the same architecture, I think the EH2 is about 20% larger, roughly. So the good news there is you're getting almost 2 cores for a little bit more than the price of 1. And that's really the key benefit here, is that if we didn't do this, the design team, if they needed 2 processors, they had to buy 2 processors. You know, this is now an option that allows us to have better innovation. And we think long-term compelling value. So again, if you take a look through here, so you know what we tried to sort of show you is that there's various buffers, and that's why there's like the blue here as well as the green boxes here, where there's kind of 2 sets of what I was talking about before in some of these various registers, buffers, and other functionality, and that allows the 2 threads to operate. So you know, some of the further details here on the instruction buffer, right? So each thread has 4 instruction buffers, right? Each cycle up to 2 threads. So you know, what's interesting here is that, you know, one pipe can implement an instruction and a thread, and then actually that thread can jump over to this pipe if you know, this one's waiting for something. So it's kind of interesting in terms of the flexibility. Oops, I didn't mean to do that. Let's go here. Okay. So, all right, let's start with this question. There's not. This is just kind of an example of code and how it could be run. So there's an arbiter at the beginning that, you know, starts to feed the threads in here, and then you get to this 3rd stage here where we're able to have multiple threads decoded, aligned and decoded. And sort of what this is kind of showing you is that you have these green and red thread both running, and you know, the red thread gets fed into this pipe and the green over here, and maybe this pipe is waiting for something, so the green jumps over here and then it jumps over here, whereas the red is here, and then, you know, it executes and jumps over. So, or this had to do a some kind of load store. So this it's kind of a you know, a feature set of the superscalar architecture that was put in to support the multiple threads. So, you know, the real key benefit is what we're able to achieve out of it. This is actually a sort called MSort example. And what's interesting here is when this is done, there are these various IO calls and other commands that you were waiting for, maybe using the multiplier or loading some information from external memory, what have you. So the instructions per clock cycle is, you know, 0.79 for a single thread, and you know, that goes up to 1.5 for multi-thread. So, you know, again, we're just sort of showing you, now this is obviously a good example for us that leverages, but it is one of the things that we do in our architectures and in applications. Let me show you some data across what I think is very representative. And let me explain this chart to you. So on the left, let me go over here. Okay, so this is the number of multi-threaded instructions per clock cycle. So, you know, it starts at 0, and then here's 1 instruction per clock cycle, and then there's 2 instructions per clock cycle. That's what this axis is about. And then over here this is the single-threaded performance. So, you know, what you find here is, if you're running at, you know, 0.2 instructions per clock cycle, you should be at 0.4. You should be double that, right? When you're doing dual threaded. And so we ran a number of different applications and software. And so if you look between zero, well, it's not zero, but just over 0 instructions per clock cycle to a half, we were able to get nearly a 2x gain, which is what you expect. This is like kind of perfect. When the instructions were half an instruction per clock cycle to 1 instruction, just under 1. So like in this range here, so for these here, these are all data points that we're able to actually, we don't quite double, but we multiply times 1.83. So, you can see at 0.6, there's a number of implementations, like 1 instruction or 1.1, 1.15. So, a pretty interesting cluster here. This green dotted line is the ideal. Like if the core was perfect, if you engineered it, 100%, and obviously that would take more silicon and power and so on. But this is a really great, implementation. And even as you go above 1 instruction, so now it starts to get harder, right? Because, the limit is 2. So, as you get to like 1.3, 1.4, you can't get over 2. So, but we're still boosting the performance 36% there. And even over 1.5, it's still a 10%, 11% bump. So as the instructions per clock cycle are low, whoops, didn't mean to do that. As the instructions per clock cycle are low, we're getting a, between 1.8 to 1.95, effect. So a really good performance here. And that was, if you remember way back towards the beginning when I talked about some of the challenges, this is something that the Swerve core addresses for us. Okay, so let's see here. So just to talk a little bit further, so we taped out the first SoC based on a Swerve core, and it's a controller. It has these types of interfaces. Can't get into too many more details. And we also wanted to make sure that everybody knew that Codicip does support this architecture. So if someone's interested in Swerve, you can go to the GitHub, you can download it. But if you want to commercially use it and you want some professional support, Western Digital is not an IP company. We've worked with Codicip, though, to get them trained up. And they have actually, I'm happy to say, a number of engagements ongoing. Swerve has really started to pick up momentum, and we're thrilled that it helps accelerate RISC-V. This is kind of a little bit more of sort of where we see things going. And what you can see here is most of our architectures, we have like a main CPU and this data path processor. So the main processor tends to interface with the host, in terms of commands, and also with the, some housekeeping functions. The data path, just like it says, handles the back and forth encryption, other functions. We are also looking at cores to implement root of trust and other security provisions, state machine, and so on. So we can envision a time where there's going to be multiple architectures. Whoops, my mouse is a little jumpy there. And so for those of you who do want to do development, or you want to kind of get more into or understand the Swerve, you can join CHIPS Alliance. You don't even have to be a member. You can participate or listen in. The CORES working group is pretty active. It meets a couple times a week. These are some of the companies that are part of CHIPS Alliance. I think there's 1 or 2 missing, but you get a kind of an idea here of all the organizations that are participating. Not all of them, have input on Swerve, but a number of them are working on it. So that's just something to make sure you keep in mind. And kind of this brings me to the end, and I'll kind of conclude here and turn it over to Kunling and John. So we made a commitment back at the end of 2017 that we were going to be moving all of our architectures, and this is demonstrated proof that that's going well underway. I would actually characterize it as. The second generation of cores, were very exciting for us to be the first commercial dual threaded and the really low power EL2. And this RTL, it's in the GitHub community for Chips Alliance. And what I'll do is before I send this Kundan to you, I'll put in the exact links for all 3 cores. So it's just easy for people to jump to the one that they want. And then I'll just leave with this slide. If you want to get in touch with me or connect, I'm basically active on LinkedIn. This is my LinkedIn handle. My Twitter handle is Teodoro J. That's actually my real name, is Teodoro. So maybe that should be a trivia question in the future. Let me see, we got a question here. Are these cores available for other people to make their own? Rumi, the Swerve cores are readily downloadable from GitHub. You can get the source code and you can modify them if you want. That's the short answer is yes, they're available. And you can do a number of implementations. I know that there's some open source organizations in addition to Chips Alliance that have actually used them and have targeted other tools. So for example, there's actually an open source SOC building tool called Fuse SOC, and they've actually incorporated Swerve into that architecture. So you could go in and do an open source implementation and target it to an FPGA, for example. But anyway, this is the contact info for me as well as for staying in touch with RISC-V. Have you guys tried vector extension on EH2 or plan to do that? So I don't have the exact answer for you on that. Vector is a really interesting area. That's kind of how what I would say right now. But I don't have a definitive answer for you. If you want to follow up separately, we could talk. Okay, I think I'm done. I'm probably over my time limit or close to it if we want to keep it going. So let me stop this share.
Great. So if there are any additional question for Ted, feel free to put it on the Q&A, and then we can keep answering as we go along. So